and get started. Yeah, all right. We're very happy to have Sebastian Ellis here today. He's been here, I guess, almost a week now, visiting us at NYU. It sounds like he's going to stay in the US just a little bit. We're going to Minneapolis soon, but he's going to tell us about some gravitational waves and how well, I guess, we can really measure some of these high frequency gravitational waves experimentally in the future. So without further ado, Sebastian, take it away.
Yeah, thanks, David, for the introduction, and thanks everyone for hosting me this week. It's been fun trying out different foods. Yeah, so I'll give a relatively informal seminar, and I really mean informal, so please interrupt me and ask questions if there are things that are unclear. And as you can see from the title, I'm going to be discussing the detection of gravitational waves, mostly from the classical perspective, but I'll also give a little bit of a hint towards where quantum limits lie for detection of gravitational waves and what they mean for our ability to search for the most interesting signals. So if you know what I've worked on, you probably know that this is going to go in the direction of high frequency gravitational waves. And so I feel like I need to motivate why one should think about high frequency gravitational waves in the first place. So I'll provide a few motivations. And by way of doing that, I will try to pass what I call the Goldblum test, which is, so in Jurassic Park, Jeff Goldblum questions why the scientists bothered cloning the dinosaurs, and says, just because you can doesn't mean that you should. And so indeed, we can study high frequency gravitational waves, we can study whether they're detectable, but the question then is, should we? And
Dinosaurs existed.
Sorry?
High
frequency gravitational waves exist.
Yeah.
As we will see. Okay.
Turn it around. Why should we study merging binaries? We know they exist.
Yeah. We want to make sure they exist the way that we think that they exist.
180 degrees. That's what we should do because we don't know any.
Yeah. Well, especially with high frequency gravitational waves,
Exactly.
We'll see. Right? We don't know very much, and so maybe there's a lot more to learn. But in any case, so I don't think we need to argue about why gravitational waves are interesting, but I would argue that, and we were kind of having this discussion yesterday at lunch, that the gravitational waves that we've observed so far only really tell us about events in the recent universe. We've seen gravitational waves emitted by merging black holes. Whether the PTA signals hold up or not is a different debate. But if they do, probably the most simple answer for what they are seeing is mergers of supermassive black holes. So still relatively recent universe events. But we know that owing to the weakness of gravity, that if gravitational waves are produced at any point in the evolution of our universe, then the universe would be transparent to those gravitational waves. And so if we were to detect them today, we would be able to infer something about what happened in that early time. And the thing that is exciting to me about this, of course, is that this allows us in principle to access much earlier times and much higher temperatures and energies than what we can access through photons. Of course, through photons, we cannot see beyond the cosmic microwave background, which in and of itself gives us a lot of information, but we'd like to see really what happened in these stages, and not just through a snapshot, say, at BBM. And gravitational waves provide us a means of accessing this information. So I should say a few words about the spectrum of gravitational waves, and in particular, since I've just mentioned gravitational waves being emitted from processes in the early universe, I would like to point out for maybe those of you who are not completely familiar with this topic, that when it comes to cosmogenic gravitational waves, there is usually a one-to-one correspondence between the temperature at which the gravitational waves were emitted and the peak frequency that we would observe today of those gravitational waves. Meaning that as you go to higher and higher frequencies, you're also going to higher and higher original temperatures at which those gravitational waves are emitted. And so in some sense, you could argue that probing high frequency gravitational waves is a way of probing very high energies and very high temperatures in the early universe, which would be inaccessible to us with colliders on Earth. That's, of course, the case for cosmological gravitational waves. When it comes to astrophysical gravitational waves, there is again a one-to-one correspondence between the frequency of the gravitational wave emission and a scale associated to the system that generates those gravitational waves in the first place. So the classic case being if you have a binary system of black holes, then sort of the peak gravitational wave emission occurs when they're relatively close together in a relatively tight binary, and then you can just get the gravitational wave frequency from some number of Schwarzschild radii through the usual Keplerian orbit law. So when it comes to stochastic gravitational waves, like I said, there's this relation that more or less tells you that the peak gravitational wave frequency, if it was emitted in the early universe, scales like the temperature. So here I've normalized to the temperature that would correspond to a signal in the least Hubble. Sorry?
Is it just Hubble or not?
It's the horizon scale.
That's what I'm saying,
yeah,
Hubble.
Yeah.
So frequency is just Hubble.
Yeah.
At the time of emission.
Yeah, and then it's redshifted to today.
Right. Redshifted, of course,
Yeah.
right. Okay.
Well, it depends on the source too, though.
Yeah, it does depend on the source.
It's the scale size of the source.
Scale factor on.
Yeah,
right?
like, yeah.
But to order of magnitude, it is always just Hubble.
Sometimes no, like, I mean, cosmic strings, the scale size is much smaller than Hubble.
But then this relationship will break.
Yeah, so then there's a spectrum, right? So then rather than being a peaked structure, you actually have a sort of broad spectrum of gravitational
Okay.
waves. So this really holds well for like a phase transition, something that really is punctual in time. It occurred at a moment in time everywhere in the universe. If you have something that is sort of occurring over multiple times, then you don't really have this relation.
Okay.
Okay, but there are actually sources of high frequency gravitational waves that are stochastic in nature from within the standard model, which provide interesting targets. As we will see, these are targets that are probably unattainable even with very futuristic technology, but they remain interesting from a theoretical perspective. So one of them is the fact that if you have a cosmic microwave background emission that we observed, and we know that it was associated to some thermal plasma that had fluctuations at some particular time, and that thermal plasma actually also emits gravitational radiation. As you can imagine, the amount of gravitational radiation being emitted is not enormous. It depends on the amplitude depends on the peak temperature that the universe ever reached. So in the top right there, you see this plot from Ringwald et al. From a few years ago, showing that the peak amplitude is, something that you might think would be detectable if you just extrapolate horizontally. That's a very dangerous thing to do. But that corresponds to M Planck, which is unphysical. So we know that that is a little bit of a difficult target. The peak frequency actually depends also on the number of degrees of freedom at the time. So there's some flexibility there, but not a huge amount. There's an analogous emission of stochastic gravitational waves from basically every star. Of course, that would be dominated by the nearest star to us, the Sun, which is just that fluctuations of the solar plasma also emit gravitational radiation. It also follows a roughly thermal spectrum from inheriting the thermal properties of the plasma that generated it. And there, the peak frequency is of order keV or so.
What's the strain, roughly, for the solar?
It's even smaller than the cosmic gravitational microwave background. And further to the right, which makes it even harder to access.
But I think it is remarkably large. If you express it in like ergs per second, it is something like 10 to 20 or something. I don't remember. Weinberg, I think.
Yeah,
computed.
there's like the power of Berkeley in 1970 or something. He comments about it because he was at Berkeley then. So like around that.
Yeah, so the original calculation was Weinberg in 72.
Yeah.
And yeah, he does comment on it in physical units, so like ergs per second as opposed to strain or something else.
Sorry, I'm still a little confused about the frequency temperature relation. Like, it's definitely the case for thermally produced gravitational waves,
Yeah.
but like for sound
Sorry,
waves.
which one? This one or
Yeah,
that one?
the yeah, that expression, because like sound waves or turbulence in a phase transition are going to be over Hubble, which is like T squared over M Planck, not
Sure.
T, right?
Sure. But this is for the peak, not from the sound waves or the turbulent production, right? So just from the bubble collisions.
But actually, sorry, I also don't understand now, because h squared is t to the 4, right? So
Yeah.
shouldn't it be t squared? So it is something else. So it is not just Hubble.
It's not.
Like there is that factor, like a, their characteristic scale relative to the horizon, but it's usually like 100.
So it should be t squared temperature.
No,
If it is Hubble, then
No,
it is t squared, that's
it's
for
not
sure.
It's not T squared.
But this one is just thermal
Yeah.
scattering.
Yeah,
Yeah.
it's gravitational
So it's not-
pressure.
Oh, yeah, that I agree.
If it is thermal, that's one thing, but then it is not Hubble, right? If you have.
Yeah, there is no
It's it's Hubble, which is proportional to t squared at the time. of
Oh, yes,
emission, but then there's
redshifted would
redshifting.
take
Yeah,
back one Hubble. Okay, good, thank you. We have done something.
But so to make this point is simply that if you measure gravitational waves at high frequencies, you're probing BSM cosmology, right? We're probing very high temperatures indirectly through the gravitational emission from whatever happened early in the universe. When it comes to astrophysical gravitational waves, like I mentioned, you can think of binary and spirals, where here there's a sort of almost one-to-one correspondence with the scale, not quite, because there's also the dependence on the size of the binary. But you see here that I've normalized the frequency of emission such that I get something in the order of gigahertz, which would require a binary mass that is much, much less than a solar mass. The reason that I've normalized it to that particular value is because I have in mind experiments that are sensitive in the gigahertz range. And what this is telling us is that if one were to detect a signal, you'd be probing something that comes from beyond the standard model. The standard model, as we understand it, does not produce significantly subsolar black holes. And in general, any gravitational wave emission from binaries that is above a few kilohertz, or maybe 10 kilohertz in the case of binary neutron stars, would correspond to something whose mass is much less than a solar mass, and therefore presumably comes from beyond the standard model. And then another, in some cases, more speculative example of gravitational wave emission that can come from astrophysical sources is from superradiance. So if you have superradiant boson clouds, which I think this audience knows very well about, then you can also get gravitational wave emission from annihilation and decays of the bosons in those clouds around these black holes. And there's a one-to-one correspondence between the gravitational wave frequency and the mass of the boson, which is in turn related to the mass of the black hole around which it has accumulated. And so once again, if you want to have a sort of order gigahertz signal, so here I'm normalizing to the not innocuous choice of micro EV, motivated by, say, axions, then this would also require a subsolar mass black hole. So that, in that case, would be BSM squared in some form of BSM power counting, because I require not only one element beyond the standard model, but now a second element beyond the standard model. That said, if I go to lower frequencies, we've found that you can indeed still have supra kilohertz signals from only one ingredient beyond the standard model, where the host is a normal astrophysical black hole. But that requires being only a little bit above this sort of kilohertz regime that I would argue is the natural boundary between SM and BSM astrophysical gravitational waves. So another reason to consider going beyond kilohertz frequencies is simply astrophysics, actually. What have we already seen, and therefore what can we hope to see in the future? And in particular, when it comes to cosmogenic gravitational waves, which will produce a stochastic background. So here I've taken a plot from the Nanograv collaboration showing their data points in terms of strain as a function of frequency. You see their sort of best fit model, which more or less matches what they would expect from mergers of supermassive black hole binaries. And what I want you to take away from this is simply that if they have indeed observed this signal, then there is an irreducible foreground of stochastic gravitational waves that they have already observed. Meaning that if you have a signal that lives down here, it is going to be rather difficult to see that above this astrophysical foreground that is already in your data set. You can extend this to higher frequency detectors. So here now we're showing the LISA band. So that black line that sort of looks almost like a quadratic potential in the middle there is the LISA sensitivity curve, assuming only noise from the detector and from the environment. But then you have to take into account the fact that there is an expected foreground of white dwarfs that are just in binaries twirling around, both inside the galaxy, which is the orange curve, and outside the galaxy, which is the red curve. And so between these two, once again, you have an astrophysical foreground, which means that if your signal lives say over here at an omega GW of order 10 to the minus 12, you've got to sort of do almost 1.5 orders of magnitude of archaeology through this foreground to actually get to that interesting DSM signal. Finally, the situation is not quite so dire for LIGO, but here maybe you've got less compelling motivations than in the LISA band to expect a stochastic background from beyond the standard model. But here you once again have the same situation where you expect to see astrophysical foregrounds with some amplitude. And so if you were to go beyond these sensitivities, so this is for LIGO and its eventual A LIGO design sensitivity, there are other proposals like Cosmic Explorer and ET that plan to go even further into this parameter space than what's shown here. And this would suggest that they will see these astrophysical foregrounds from unresolved binary black holes and binary neutron stars. And you would have to go digging through that foreground in order to find a cosmogenic signal that you would be most interested in as a particle physicist.
Why do you say less compelling for LIGO?
What's less compelling? Sorry.
You said
just because just because this is not like way up in the design sensitivity curve, right? It's sort of at the edge, meaning that you could have a signal that goes above here that would still be detectable by LIGO, right? Yeah. So it's not the same as in LISA where the foreground is way above the design sensitivity curve. So in some sense, the astrophysicist here is Buzz Lightyear saying, look, we're going to see all these signals. And we, the particle physicists, are woody thinking, oh, crap. And finally, a much more mundane reason to consider looking for high-frequency gravitational waves, but one that I would argue if people are investing in these things is nevertheless worth doing, is that many different proposals have been made for experiments to look for light-dark matter using all kinds of different technologies. And it turns out that basically all of these have interesting sensitivity to gravitational waves, as well as those dark matter candidates. So if you're already running your experiment that's already been funded to search for light dark matter, you may as well do a secondary search looking for gravitational waves, and maybe a couple of extra PhD students get theses. Okay, so having gone through that introduction, I'm going to now discuss sort of very heuristically how gravitational waves can be detected and what we can infer about the prospects of their observation given these heuristics. So as we all know, when a gravitational wave passes by, if I have two masses that are in free fall, then we know that those masses are going to move relative to one another in the presence of that gravitational wave. And so you can think of a gravitational wave measurement, therefore, as being a measurement of some sort of displacement. So if you go away and ask your favorite AI tool, what is the SQL for displacement, where SQL stands for standard quantum limit, then you probably get an expression like this being spat out by Claude or ChatGPT or what have you, where m is the mass of the test mass in free fall, omega is the frequency of the signal, and gamma here is the width with which this mechanical object dissipates energy. So maybe it's a broadband detector and that width is just omega. Maybe it's a narrowband detector, in which case that is an omega over a quality factor. But there's some stuff that's been hidden behind the hood for where you get this SQL from. And in particular, it comes from the fact that in order to make this displacement measurement, you need to imprint the movement of your test mass onto photons that are inside your detector. So you can think of this, for example, as being the case for LIGO, where you have test mirrors at either end of your long arm, and you send the laser back and forth, and you're actually imprinting the movement of the test masses onto the laser, which you then go away and measure, and you observe that there's a phase shift or a shift in the power if you want to do that kind of measurement. So if you had taken the SQL formula and you'd said, okay, it depends like one on mass, which means that if I take the mass to infinity while keeping the size of the apparatus the same, obviously an unphysical limit, but let's just take it for the sake of argument, then you would think you would have a perfect measurement, that you would have no error in your ability to measure these displacements. And that would be wrong, because what happens when you send the mass to infinity is that you're only turning off one of the irreducible noise sources which is the back action coming from the fact that you're measuring the motion of this test mass with photons that is then imprinted back on the photons. So you're only turning off one of the two sources of noise that when combined gives you the standard quantum limit, but you're still left with the imprecision noise associated to the photons themselves with which you're doing the measurement. So again, using the example of LIGO, you can think of, if you've heard of the word shot noise, that's this guy, the imprecision noise here. Yes, Marcus?
Sorry, you might have already mentioned this, but just for the roadmap's sake, you're going to argue that some future detector or LIGO or whatever is hitting a quantum limit, and I should worry about this.
LIGO is already at the SQL and
already
even
at-
beyond at in some frequency range.
Okay.
So what I'm trying to derive here is an SQL for different classes of detectors. So we'll go through that in a few steps in a moment. And in this unphysical limit where I'm going to take my mass to infinity so that all I need to worry about is the imprecision noise.
Sure.
Now, it turns out that that is actually a reasonable limit for the high frequency regime, not the low frequency regime. The reason being that I have my sort of back action noise that goes like this in LIGO, let's say, and then I have my shot noise that goes up like this, right? So this is
Access this frequency.
yeah. So here I have noise equivalent strain in units of per square root hertz. Here I have frequency in units of hertz. And so the SQL is this point here where they match. And so that's why people say, oh, I can scan the SQL here by changing the power, basically changing the photons that I'm using to make my measurement. And so what I would say is that this being the imprecision noise means that in the high frequency regime, I can basically take my mass to infinity limit and just consider this part of the noise. So that's what I'm going to do next. Okay. So having taken this mass to infinity limit, then all I need to consider to understand the imprecision noise is the stored electromagnetic energy in my detector. I can ignore now the mechanical energy in my detector completely. There are specific situations where that won't be the case, but we'll discuss them when they come up. So very schematically, the stored electromagnetic energy in my detector goes like the square of the electromagnetic field times the volume of my detector. And in the time domain, that's not a particularly instructive way of thinking about things. But in the frequency domain, we can see maybe a little bit more clearly what's going to happen when a gravitational wave affects this measurement. So I can expand in powers of the strain h, and I will find that there is a first order term, which is an autocorrelation function now in the frequency domain of the background EM field that I have, which has some frequency spectrum as a function of omega, and the signal field that is now linear in h. So EH means that there's a little h in there times an E naught. So there's that linear piece, and then there's also a quadratic piece, which is just, I'm dropping the E naught guy and I'm going to the second order in my H expansion. So at first glance, you might think, okay, well, why would you even bother going to the second order term? We know that H is very, very, very small. So clearly the first term is going to
understand why are you computing this energy, much less why you compute the perturbation to this energy.
Why am I computing the energy?
Yeah, indeed.
Because the energy
My
is,
purpose is to understand some error, right?
Yeah.
What do I care how much energy there is between the mirrors?
because the energy is related to the number of photons that's inside my detector. And if those photons,
So ultimately you will bring it to the air.
yes.
Okay.
So if you want, the very short version is shot noise is associated with the fact that the photons in my detector are Poisson distributed, right? Because it's a coherent laser field. And so they go like the energy to some power, and we will see what power that is. And that's why the energy in my signal needs to then be compared to the energy in my background to find where the limit lies for a classical detector. Okay, so this linear signal is, for example, what you would measure in an interferometer, right? We know that LIGO is measuring things that are linear in strain when they do a matched filtering analysis for a gravitational wave signal. But we also know that if you take, for example, an axion experiment searching for dark matter, then they're doing a measurement of power, typically. And so they're actually measuring this quadratic signal. So does that mean that the axion people are way off base and they should have been doing a linear measurement all the time because they would have been much more sensitive? The answer is, of course, no. And we'll understand that in just a moment. So let's first consider the worst type of the two detectors, or at least on the prima facie worst type of the two detectors, which is the one that is quadratic in the gravitational wave H. So in the frequency domain, I can think of performing an experiment where I have some number of photons or some energy in my detector stored at some frequency. So maybe that is a static background magnetic field, for example. So I'm still abusing notation by using E, but just think of it as a static E and M field at 0 frequency. Or maybe it's some oscillating background at some frequency that is very, very small compared to the frequency of my signal. And so when my gravitational wave comes in with frequency omega g, I'm going to get a new spectrum of the electromagnetic field at the frequency that is associated to omega g plus or minus the background frequency omega, whatever that might have been, whether 0 or non-zero. And so I end up in this situation in the frequency domain where my signal field is very far separated in frequency space from my background.
This is how they do axions, right?
This is how they do
They
axions.
measure the intensity of the alternating current in a DC magnetic field.
Exactly,
Right, this-
exactly.
okay.
So this is typical of an axion experiment. And so in this regime, what you could argue is that they do an experiment that is almost background free. And I say almost because there's always an irreducible number of background photons coming from quantum mechanics, which tells us that you can't do a completely background free experiment. So more specifically, the power spectral density of noise, if you are purely quantum limited, although I'm allowing here for the fact that there might be some thermal noise as well, is given by that expression there. And so you can see that in the high frequency limit, where high frequency means omega much greater than t, this scales like omega. So that's the sort of shot noise that you would expect. And meanwhile, in the low frequency limit, then this just looks like temperature. I can write what the signal power spectral density looks like very schematically for a quadratic measurement. So I've got 2 powers of h there. I've got the background stored energy of my experiment. And then I have this transfer function, t quad squared, which I will explain in a moment. That basically tells you how your detector actually responds to your signal, right? You could have a poorly designed detector for which that transfer function is just 0. But you can have a very well-designed experiment where that transfer function can be very large. And then there's some factors that account for the fact that this signal could have some width. Here I'm modeling it as a top hat with some width delta omega. So if you go away and plug this through your SNR machinery, what you find is that for a classical detector operating at the standard quantum limit, the minimal detectable strain that you can achieve scales like 1 over the square root of the stored electromagnetic energy times some factors associated to how long you search for and how big a bandwidth you can search in or how big a bandwidth your signal is in, and then 1 over this transfer function. Okay, so unsurprisingly, something that is quadratic in H, the sensitivity scales like 1 over the square root of the stored electromagnetic energy. So now the question is, what happens if we do a linear measurement?
Sorry, just one comment. So that's why this guy Lyman Page or whatever wants large magnetic field inside his detector. Remember, have you been here for his talk? Right?
No, I was not here.
Right. That's why they put this axion detectors in very, very large magnetic fields.
They're maximizing this.
Right.
And not worrying too much about this, basically. Although the quality factor in cavities is in the transfer
They do
function.
both.
Yeah, so they do both. At the cost of changing the bandwidth. So we'll see how that has an impact later. Okay, so before we do the linear detector, let's just imagine what would happen in a quantum regime. It's not necessarily the best quantum regime, but it's one where I've reduced my noise from the shot noise limit to basically 0 photons, right? I'm doing this by maybe having a single photon counter that has a really, really low dark rate. Whether that's achievable or not, who knows? at these frequencies, at some frequencies, maybe it is, but at low frequencies, it's quite difficult. And so now I'm just requiring that I have at least one photon of signal in my integration time to say that I have made a measurement. Now, from a statistics perspective, that's not enough to say that you've detected something, but just for the sake of argument. And so in that case, what you find is that this best possible sensitivity for this quantum detector would be for a quadratic detector, again, scaling like 1 over the square root of the energy. And the difference with the previous slide is just how the integration time and the bandwidth factors come in.
So is it like the previous formula? Can you show that again?
Yeah,
So that like saying the bandwidth is 1 over t?
Yeah,
Okay.
exactly.
But it's still not the best
It's not the
thing
best
you
possible thing you could do with a quadratic detector.
Yeah, because you could do with entanglement or squeezing, you could.
Yeah, so we'll get to that with the linear detectors because it's easier for those cases. It's still a quadratic measurement in the sense that you're still doing a 2-point function measurement, but you can do an interference where you take 2 linear pieces and interfere them. Anyway, I'll do the linear detector next, and maybe that'll be better. Okay, so in the linear case, what you have is a background E&M field oscillating at some frequency omega. But if you want that 2-point function at the top there to be non-zero, it means that it also has frequency space overlap with your signal field, right? So this is the case in LIGO, where your signal is at 100 hertz, and it's modulating a terahertz laser. So there is no separation in the frequency domain between your carrier and your signal. They're sitting on top of one another, and so this 2-point function is non-zero. And what that means is that also in the same frequency range, you have a non-zero 2-point function of the background field with itself, right? So you actually have an enormous number of background photons hitting your detector, which is very roughly the stored energy times the integration time of your experiment is the total number of photons that you would expect hitting your detector. So now you have, for this linear measurement, a noise PSD that scales like the square root of stored energy in the numerator, which is just the square root of the number of photons when you account for all the factors of omega. Your signal PSD is linear, right? So we now have a transfer function for your linear detector, linear in H, linear in the stored electromagnetic energy, and again, the stuff that accounts for the bandwidth. And what you find is that your best possible sensitivity for your classical linear detector once again scales like 1 over the square root of the stored electromagnetic energy, and has exactly the same scalings with delta omega and T-int as we found for the quadratic detector. And now the only difference is that this is a linear detector transfer function versus a quadratic detector transfer function. Okay, so interestingly enough, what you find is that the classical detectors, whether you do a linear interferometric measurement or a quadratic measurement, power measurement, they have the same sensitivity. Now, this is making very strong assumptions about what is achievable by the detector. So there are good reasons to do one versus another in various different setups.
Sorry, what exactly do? You design detectors or?
I think about detectors. I don't necessarily design them.
Like, is this new? Because it sounds like it is something from the book of Khalili and Braginsky or whatever.
Yeah, you probably can find this in some paper by Braginsky for the linear detectors.
I just want, I'm curious, what does it lead to, all these arguments? You will propose a new detector?
No, I will say what we can detect in the future.
Regardless of by what detector?
Yes, I won't care about how what detector it is, but I'm going to use some of these scalings to show what could be achievable given certain assumptions.
Okay.
On the detector side. Okay, so indeed, as Ken mentioned, there are other quantum games that one can play. So for example, if you go to the Heisenberg limit, this means that you're harnessing all n photons that you're using in your measurement. So in the case of LIGO, this would mean that all of the n photons in the laser are entangled or in a Fock state or in some very special quantum state. And then you would get a scaling that goes like 1 over the stored energy. So obviously that's a massive parametric improvement compared to the classical detectors. That also requires that you have absolutely no losses anywhere in your detector, which is presumably unphysical. So perhaps a more reasonable quantum regime is one where you squeezing your vacuum to the absolute limit. And there actually, Brzezinski and Caves showed that you get this U into the 3/4 scaling for your sensitivity. There they talked in terms of the number of photons, but you can rewrite it as UN. Yes.
What would the squeezing look like in practice? Like what are you actually doing to the experiment?
So you are actually using nonlinear, what's it called? So in LIGO, what they do is they insert nonlinear, using nonlinear devices, they insert squeezed vacuum states into the output port. So basically the loss port of the detector. And so what this does is it puts some of your error into one of the two quadratures of the photons. And so then you measure the one that you have less of the error in.
Okay. So somehow you.
Yeah, we can discuss later how exactly
In two
it's
conjugate variables, right?
Yeah.
If you're interested in the phase, you
Yeah,
can squeeze
yeah,
the area
yeah,
of the
yeah.
phase
Yes, yes,
at the
yes.
expense
Yes,
of larger
that
area.
makes sense. Yeah.
Okay. So there are various different details that I've ignored so far, in particular the transfer function. But the takeaway should be that the best classical sensitivity that you would expect scales like 1 over the square root of the number of resources that you have. And the number of resources here is the stored electromagnetic energy and the integration time. Okay, so now in the time that's remaining, I'm going to discuss some of the transfer functions that we've thought of, and then put them to the test in terms of how we'll be able to, whether we'll be able to probe stochastic gravitational waves in the near or far future.
So, Sebastian, before you go on, you're restricting yourself to these electromagnetic detectors, right? Cavities and interferometers.
No, it also applies to optomechanical devices or to Weber bars.
But in what sense is UN then the stored electromagnetic energy? Let's say if I have a resonant mass detector that.
Yeah, so on the resonance, this no longer applies, and you replace the stored electromagnetic energy with the stored mechanical energy. If you want, we can discuss later how that happens.
But the stored it's just a aluminum chunk sitting there in the vacuum. So, and what is the stored mechanical energy of such a
so any object that can vibrate at some frequency omega is going to have an associated energy that goes like m omega x squared.
Yeah, but the initial it's not in a perturbed state, right? When they do x is 0 in some sense.
Yeah.
I mean,
it's when I say the mechanical energy, what I mean is the capacity for that thing to have an associated mechanical energy when it vibrates at a frequency omega. Right, so it's just
confusing.
But what about the amplitude?
Yeah, exactly.
Yeah.
Like
so that's the max. That's what you would have with amplitude 1, and that's what ends up entering that formula. But then, of course, your actual signal energy.
What do you mean?
What is
amplitude
X?
1?
What
The
is-
elongation of order 1, like aluminum bar.
Yeah. So x here would be the length of the bar, right? That's the maximum accessible energy in some sense, right? So you're really deforming this thing maximum, which you never do in practice. But that's sort of a measure of the maximal stored mechanical energy in the detector. Okay, so
Sorry guys, I don't understand your discussion at all. So are you claiming that even if you don't have no photons, whatever, if you have this Weber or whatever, this bar experiment,
mechanical bar.
your formulas still somehow magically apply?
So this formula applies away from the mechanical resonance for a Weber bar, for a resonant mass detector. On the mechanical resonance, it's no longer the electromagnetic stored energy that is most relevant. It's actually the mechanical stored energy.
And by mechanical stored energy, you mean this
I mean
crazy
this.
expression.
Yeah,
Okay.
exactly. So maybe I should rewrite this as U max. But it enters the same way, so it's still 1 over the square root of U, whether it be electromagnetic or mechanical, depending on which regime you're in. And there's always this 1 over transfer function. Okay, so let's discuss some experiments in the time that remains. And let's start with perhaps a less obvious one, which is interactions of the gravitational waves directly with the light inside your experiment. So now we're kind of actually going one step back from what I had in the beginning, where I had masses that were vibrating in the presence of the gravitational wave. Here I'm imagining the gravitational wave just couples directly to the photons and imprints the vibration on those photons. So if you start from the Einstein-Maxwell action, you go away, you compute an equation of motion, what you find is that you can write the equation of motion such that there's an effective current involving the background of gravitational waves h here that can source electromagnetic fields, right? So in your Maxwell equations, you would have your usual currents, and then you would also have this additional effective current in the presence of the gravitational waves. So you can use that to go away and compute here very schematically. In some of the papers that we wrote, we did it much more carefully, what you would expect for your transfer function for this type of detector, this type of electromagnetic detector where you have an interaction of the form shown in that cartoon there. So in the top is the equation of motion in the frequency domain. Here I'm very schematically giving what the coupling of the gravitational wave is to the EM fields. And you can use that to go away and solve that equation of motion for the transfer function squared, which has this rather awful form. But we can consider limiting cases of that form, particularly starting with a well-known type of experiment, namely an axion cavity experiment. And so here in this paper from a few years ago with Asher Berlin, who used to be a postdoc here, we computed what the signal sensitivity, what the sensitivity to gravitational waves would be if the gravitational wave were monochromatic and continuous. So this would not be your prototypical binary black hole merger, which actually scans frequency as the binary evolves. It would be something more like super radiance. And what you see is the strain sensitivity is on the order of 10 to the minus 20 ohm. And here the transfer function that you would get is from that nasty formula on the previous slide. You find that you're in a regime where all of the omegas are the same. There's no big hierarchies. And so you get a transfer function that is basically just U times some overlap factor eta, which dictates whether your gravitational wave can actually couple to the EM modes in the cavity. And this factor of omega L, but for a resonant cavity, that thing is of order 1. And so for typical cavities, that's order 10 to the 5. Now, if you're more familiar with the axion signal power, the only difference between these two is if you identify the dimensionless quantity GA gamma gamma times A as sort of the effective strain, then there's just this extra power of omega L coming in that could in principle enhance your sensitivity, but in a resonant cavity is order 1 and therefore doesn't lead to an enhancement. And I should mention that one of my collaborators, Diego Blas, has set up with Dima Budker and friends an ERC synergy grant to use cavities to search for gravitational waves. So that L growth, that omega L factor that appeared that was different from the axion case can actually be understood quite straightforwardly if you just consider axion conversion in a background magnetic field and don't think about the experiment around it for now. So if you start with an axion, what you would find typically is that you get an axion-induced electric field that scales like this dimensionless quantity G times A times the background magnetic field, and then it's oscillating at some frequency. But if you do the same calculation in the transverse traceless gauge for a gravitational wave, what you find is that the induced electric field scales once again like the background magnetic field, the strain here, H, whether it's the cross polarization or the plus polarization, and there's this additional factor of omega X. And this is simply a reflection of the fact that the graviton associated to the gravitational wave is massless. The photon is also massless, and so you actually have in vacuum mixing between the two states, because there's a resonance associated with the fact that they're both massless everywhere in space. And so in the small distance limit, that just looks like the first term in a sign expansion, and so you get the omega X associated with the fact that these things are actually trying to oscillate into and out of one another as states as they propagate through your magnetic field. So with Valerie Domke and Joachim Kopp, we looked at whether this could be leveraged to have interesting sensitivity using MadMax, a different type of axion experiment, after we were asked by the experimentalists to look into this. And what we found is that actually the most interesting mode of operation is to take out all of the disks. The reason being that if you take out all of the disks, so you don't get the enhancement factor that you would get for axions, you still get this 1/f scaling of your sensitivity associated to this vacuum conversion of the gravitational wave into photons throughout the length of the magnetized volume. If you insist on having disks, you can get a modest enhancement. So that's the purple line on the right-hand side there. But it requires not only precise spacing of the disks, but also precise thickness of the disks for every resonant frequency that you want to scan, because you have an ultra-relativistic signal in your detector. So that's not an optimal way of doing things.
Can you remind me the status of MadMax?
They have a prototype that recently produced results and set limits. And I think they are on track to be fully funded for the full version of the experiment between DESY and CERN.
Did anybody bother to transform their limits onto limits on gravitational waves?
It's not so straightforward because, well, you could for
Isn't it what you are saying, that each time I measure axions, I measure gravitational waves?
Yeah, so from the data analysis perspective, it's not so straightforward as saying I've set a limit on GA gamma gamma as a function of the mass, and so I can convert that automatically into a limit on the strain, because there's assumptions about the morphology of the signal in doing your axion analysis, and they would have to correspond exactly to the morphology of your gravitational wave signal. So in the case of the axions, right, you're assuming a virial distribution of the axion dark matter with a particular spread in the frequency domain, and therefore a particular coherence time of your signal, etc. In the case of the gravitational waves, if it's, for example, a PBH merger, you don't have that coherence time. Instead, you have something that's constantly scanning in frequency, and the scan rate near the merger phase is order 1 in units of the frequency.
But still, this is exactly what you are saying. That
yes, so they can do this, and they are planning on doing.
Yeah, but with the disks in, I mean, that's what they plan on doing anyway, right? For the
Right,
axion.
so that's
They
why
are-
we also looked at the hybrid case, where you have some disks in part of the volume, and the other part of the volume is empty. And so then they still have some broadband sensitivity. It's penalized relative to the one with no disks because you have less diskless volume.
But what I'm saying is they're planning on doing the resonance scan anyway for the
Yeah.
axion case.
Yeah.
So if that is successful, isn't then the purple case, the purple curve, the projected sensitivity?
No, it's the blue one, because the blue one is assuming that I've fixed the thickness of the disks, but I can modulate the separation, which is what they plan on doing for the axion search. Whereas the purple one is assuming that for every frequency or every frequency jump that you make, all of these little sort of discontinuities, then you have a different disk separation and a different disk thickness.
So the broadband case is the dotted thing that overlaps with the purple?
The blue is the hybrid one, the blue dashed.
Okay.
So that's the one where you have disks in part of
Yeah.
the volume and the
Yeah.
rest is empty, which is what will actually happen in the
Okay.
experiment. Okay, so here the transfer function is just that omega L, and if you're on the resonance, you get an extra factor of n disks, but it's not really optimal to do that. So I'm starting to run out of time, but let's briefly mention the original test case that I had, which was the gravitational interacts with matter. Yes.
Sorry, could I just, so if I look at like a cosmological scenario, like I'm really lucky I have PBHs, I have axions, and I expect super radians for these like light PBHs, like where does that fall in the parameter space? Like, are you actually proving anything interesting, or is it?
Yeah, we'll see that in a few slides.
Okay.
The answer currently is probably not. The PBH is basically, there's the extra lever arm, which is the distance to the binary. So MadMax, I have a backup slide, can probe up to 10 to the minus 3 parsecs away. But the typical expectation for the distance to a binary at the mass where you get 10 to the minus 3 parsecs is actually of order a kiloparsec. So you're quite far away from the expected signal. Okay. So I think we all know how gravitational waves affect the test masses, but just as a reminder, You get sort of a Newtonian-like force if you work in the local inertial frame or the proper detector frame. And this is actually also why I could ignore the mass, like I said I could right at the very beginning, which is that I have on the left-hand side of my equation ma, on the right-hand side of my equation m times something, and the equivalence principle tells me that those m's are the same, and so the m is irrelevant for the signal. The m is only relevant because of the noise. So, okay, I can go away and do the same exercise that I did for an electromagnetic detector, for a pure electromagnetic detector, and now look at the equations of motion in frequency domain for this mechanical transduction detector. So here you can imagine this sort of setup where a gravitational wave comes in, couples to some mechanical mode or some mechanical motion associated to this which is sort of the displacement. And that couples to two electromagnetic modes. So this is like what happens in LIGO. It's also what happens in optomechanical resonators, Weber bars, you name it. So here I get a transfer function which looks similar to the one that I had before, except I now have this additional part of the transfer function which is associated to the mechanical response of the detector and not just the electromagnetic response. So let's apply these heuristics to LIGO just to see whether we get as a sanity check, whether we get the right result. So if I assume that LIGO has 350 kilowatts of recycled power, which is roughly the right amount, and I didn't know that there was a transfer function at all, I thought it was just 1 over square root of stored electromagnetic energy, then I would get a strain sensitivity that is on the order of 10 to the minus 12 per square root hertz. Now we know that that's not the sensitivity that LIGO has. In fact, it has a sensitivity more than 10 orders of magnitude better than that. And we can understand that by remembering what regime it operates in and plugging that into our transfer function. So it's in a regime where the gravitational wave frequency is way higher than the typical mechanical response frequency, which is of order a hertz from the pendula hanging that the mirrors are hanging from. And so instead, when I go away and plug this through, what I find is a simplified expression for the transfer function squared, which basically goes like the laser frequency times the effective length, which is just length times finesse over pi squared, and so that's 10 to the 22. So taking what we knew earlier, namely that the sensitivity scaled like the square root of the stored electromagnetic energy times 1 over the transfer function, I recover what I expected, which was SH to the 1/2 of order 10 to the minus 23 per square root hertz.
Right, what's this finesse actually?
The finesse is kind of like an optical quality factor, if you like. Okay. So a different type of mechanical detector that one can consider that we proposed last year is actually just to take a Weber bar, but it's not just a Weber bar, it's actually a magnet that can also act as a Weber bar. So if you take a superconducting magnet like the one that is or was planned for ADMX EFR, I think RIP, then that magnet, which does exist, has 140 megajoules of stored electromagnetic energy. And so if you plug that into my equations from earlier, what you would find is a strain sensitivity of order 10 to the minus 21 per square root hertz up to the transfer function. And that is a frequency dependent sensitivity. So, a lot of details being omitted. So the magnet vibrates, and that vibration is imprinted on the magnetic field that is being generated by that magnet. So in terms of the transfer function that we had previously, this operates in the regime where omega-1, the electromagnetic resonant frequency, is associated to the size of the magnet, is much higher than the gravitational wave frequency, which is in turn much higher than the mechanical resonant frequency. And that hierarchy between omega-1 and omega-m just comes from the fact that the speed of sound in materials is order 10 to the minus 5, 10 to the minus 6, whereas the speed of light is 1. So plugging that in, we expect a transfer function of order 1. Doing the calculation much more carefully, like we did in our paper, what we find is, and apologies for the abuse of notation, this is a plot from the paper with Valerie and Nick Rod, where we used quantity g. G is just the transfer function here. And what you find is that indeed you get a transfer function of order 1, unless you're on the mechanical resonance, in which case you also get a boost by the mechanical quality factor. But there it's not the electromagnetic stored energy that's relevant, it's this sort of mechanical stored energy, like we were saying earlier. Okay. And so in terms of what that sensitivity would look like, here are two different scenarios, one using that ADMX EFR magnet, so 10 Tesla, a temperature of 4 Kelvin, a particular pickup radius loop, and a mechanical quality factor of 10 to the 6. And then DM radio gut is the green line. And what you see is that there's an interesting broadband sensitivity, which is comparable to your typical Weber bars on the mechanical resonances. But the interesting thing about this approach is that away from the mechanical resonances, because you have so much electromagnetic stored energy, far more than you had in a typical Weber bar experiment, your sensitivity is still pretty good. Whereas in a typical Weber bar experiment, the sensitivity was way worse because the stored electromagnetic energy there was that of a small capacitor. Okay, so furthermore, we confirm our intuition of what the strain sensitivity should be in the regime that I was indicating earlier, where omega-1 was much greater than omega-g, which was much greater than omega-n. Okay.
So there, the BBN bound is better than everything.
Yeah, so the BBN bound put onto this plane, which is kind of an unfair thing to do, says that anything above here is excluded by BBN if it happened, if those gravitational waves were emitted before BBN. Right. So yeah, you're still quite far from the BBN bound, but the reason why it's unfair to put this on this plane is because the BBN bound is, first of all, an integral is on the integration of all of the gravitational waves, right? So it's not really at a point here, whereas this is a sensitivity at a point. This is also not accounting for the integration time that you can spend at a given frequency, which allows you to dig in, whereas the BBN bound just stays where it is, right? So this is just the raw noise equivalent strain sensitivity. It doesn't account for how long you run the experiment for, how long you search for, etc. Right, which is also why LIGO can actually go to the BBN bound, because it's the same thing for LIGO that I'm plotting here, right? It's the raw noise equivalent strain sensitivity, not the upon integrating for a long time sensitivity. Okay, so in the interest of time, I won't discuss MAGO 2.0, but that was another work that we did with Asher a couple of years ago. And this basically functions like LIGO, but using RF rather than lasers, and allows you to have a much larger amount of stored electromagnetic energy, but at the penalty of being a much smaller device and having a less good transfer function. So there you see it's the RF frequency divided by the gravitational wave frequency that affects your transfer function in the broadband case, whereas in LIGO we saw that it was the laser frequency times the effective length, or 1 over the gravitational wave frequency, depending on what regime you're in. So to conclude, let me just go back to the question that I think a few people had in their minds, and Marius was asking, which is, what does this mean for the sensitivity to the sources that we're interested in? Well, there's a problem, which is that our detectors that we've discussed all seem to have a similar strain sensitivity of order h of 10 to the minus 20, maybe a little bit better than that. But if you want to measure stochastic gravitational waves, you need to measure an energy density. And the energy density in gravitational waves scales like 2 powers of n Planck, frequency squared times strain squared. Meaning that as you go to higher and higher frequencies, if you normalize to the critical energy density and you write things in terms of big omega g, what you find is that for a fixed strain, you're probing a larger and larger omega g. And so put on a rather annoying looking plot, if you show the energy density normalized to the critical energy density as a function of the frequency, you have your n effective bound, which here we're modeling as a flat line, but it's not exactly that. Here we're also showing a couple of sort of prototypical signals that one might expect. So some generic first order phase transition, a metastable cosmic string network that upon integration saturate the n effective bound. I'm also plotting the actual LIGO sensitivity to stochastic gravitational waves, which as promised went below the n effective bound. Here I'm showing what our heuristics give for their sensitivity, which, as you would expect, since we're making rather strong assumptions, is a bit better than the actual sensitivity. Then I'm showing a bunch of different experiments where I've got 2 curves for each corresponding to the expected or actual sensitivity, expected, actual, kilometer, actual is the light blue, and MAGO is the dashed orange line is expected. And then near those lines, I'm showing the heuristic sensitivity using our very rough estimates. You see that they match pretty closely. But the takeaway here is simply that aside from LIGO, nothing gets close to the unaffected bound, right? Everything is very, very far from the unaffected bound, many, many orders of
So
magnitude
it
away.
wouldn't make sense to check whether or not some axion detector has detected gravitational waves. The
No.
answer is certainly not.
Not cosmogenic stochastic gravitational waves, no. So if they came from the early universe, you wouldn't expect to see them, right?
So
Because-
only by some nearby event. or
Exactly, so
whatever.
it's telling you that only nearby events would possibly give you a signal in these experiments. So
And for those, you don't have any meaningful candidates, do you?
primordial black holes, but it's a different morphology, and so this plot doesn't really apply to that directly.
But for the PBH in spirals, I think, isn't the expectation like, it's kiloparsec, right? For the.
Yeah, that's what I was saying, that you
but-
expect,
Yeah,
you know, at gigahertz, you would expect that it's kiloparsec away. And the sensitivity that you actually get is of order 10 to the minus 3 parsec. So it's actually not so different from the 6 orders of magnitude if you
Okay.
convert into.
I'm sorry, so this is DM radio gut, or this is what are you?
No, this is the magnetic Weber bar using DM radio guts magnet.
Okay, good. Yeah.
Okay, so now let's consider some crazy classical detectors, right? So these are not real detectors, they're not real proposals. They're just, let's dial up the electromagnetic stored energy to 11 and see what happens. So if you take a magnetic Weber bar style experiment and you use the electromagnetic stored energy of ITER and you run it in broadband mode, you barely get beyond the BBN bound. A better approach is to instead use a LIGO type experiment, but where you dial up the power to that of the power consumption of New York City, so 10 gigawatts. And then you find that you can go well beyond the BBN bound, especially at lower frequencies, but you can't get much above 10 kilohertz at the BBN bound, even with 10 gigawatt consumption of your laser. Whether a 10 gigawatt laser would actually work in LIGO, I don't think it would. So maybe a much better way to go instead is to use quantum resources. So rather than just dialing up your classical detector to 11, maybe just dial it down a little bit, but manipulate the photons in your detector as well as you possibly can. And so here I'm showing two green lines which correspond to a broadband and resonant 10 Tesla meter cube magnetic Weber bar. You see that with a resonance at any given frequency, then you can probe interesting cosmological signals up to high frequencies if you are in this zero background photon noise regime that I was discussing much earlier. If, on the other hand, you use a linear style experiment, with the squeezed vacuum limit with a 1 kilowatt version of LIGO gets you that dot dashed orange sensitivity, and at the Heisenberg limit, you get this solid orange sensitivity. So I would argue that while these things are very futuristic and possibly impossible, it still points to the fact that taking a classical detector and just scaling it up is not the way to go. And instead, taking a more modest classical detector that you then turn quantum is a much better way to go. Okay, so with that, I will leave up these open questions and open to any questions you may have. Thanks.
Questions for Sebastian?
This is very depressing, no?
So if there was,
Sorry.
This was a question.
I mean, yeah, it's depressing if you think that all you will ever have is classical detectors, right? If you are hopeful that in some far future we'll be able to manipulate quantum states and a macroscopic number of them, where
Are they
macroscopic is
planning
not
to
Avogadro.
do it on LIGO? I think they are planning to do it on LIGO,
Yeah,
right?
so-
Going beyond standard quantum limits.
Yeah, so LIGO already does go beyond the standard quantum limit. They're not at this squeezed vacuum limit by any means. They've achieved a few dB of squeezing, so they get a factor of 3 enhancement in their sensitivity in a particular frequency range near their sort of best sensitivity.
Oh, they are already doing it.
They're already doing that, yes. Whether they can do it to this level, I don't know, because I'm not an experimentalist.
Like for this plot, like how far can you go in a low frequency regime? Like you stop it to the -16 in omega gravity wave, but I mean what's actually stops the brown.
Yeah, good. So it's going to be back action noise, which I've completely ignored here, right? Because here I'm assuming I can take this unphysical mass to infinity limit, and all I care is about the imprecision noise. And that's not really fair, because the back action noise, as you dial up the power, which by squeezing the vacuum, you are effectively dialing up the power. By going the Heisenberg limit, you're also technically effectively dialing up the power. You're also increasing the back action noise. And so that means that this curve, what it does is it sort of becomes something like this, right? So you get shifted, and you're not really getting that perfect sensitivity curve there. So you would have to take into account carefully what the back action is to find out what's happening in the low frequency regime. So that's why these things are very schematic, but in the high frequency regime, they do apply.
Do you have an idea for like, I mean, realistic masses where that would cut off?
Realistic masses. No, I have an idea for where the unrealistic masses cut it off, which is for this New York City laser LIGO. I think the answer was you needed like a 10⁹ kilogram test mass or something.
There's a small problem that a gigawatt laser would vaporize any.
Yes. Small problem. Yeah, originally we had a version of this plot where it was a terawatt laser, because sorry, a petawatt laser, because petawatt lasers do exist, but they exist in a pulsed mode where the pulse duration is less than the inverse duration than the inverse frequency of your signal. So that's obviously nonsense. So this was still nonsense, but less so.
Sorry to kind of nitpick, but like the benchmark cosmological signals you have here are like unrealistic by a couple of orders of magnitude.
Oh, sure.
Yeah.
Yeah, of course. I mean, this is just to give you an idea. It's not, we're not doing a careful calculation of the signal, right?
I wasn't going to say anything until you actually have lines going through the curves.
Yeah, no, sure. I mean, it's just to say that if you had a signal that saturated the unaffected bound, then it would still be difficult to probe it. That's the point that this plot is trying to make. Not that this is a realistic signal, just this is a realistic spectrum, but not a realistic amplitude, right?
And then for primordial black hole, let's say you were lucky and it was 10⁻³ parsec away. Would we have detected such a system otherwise? Because it's the masses you need to create a gigahertz signal are still, they're much smaller than a solar mass, but potentially large enough to it's in the solar system. It would be something like Earth mass, right?
Yeah.
It would gravitationally perturb the solar system as well.
Planet
9. Yeah. Planet or maybe flying through.
Yeah.
Would we know otherwise?
Yeah, I think we would, and even for that mass, probably for the mass that corresponds to. So let me just go to that line.
Isn't it 1,000 AU or something?
Here we go. So that 10⁻³ parsecs. It's not even 10⁻³. It's like 3 10⁻⁴. Is for about 10⁻⁵ solar masses. So it's fairly light. I don't know if that would be enough to
It's like Neptune. 10⁻⁵ solar mass is Neptune.
Neptune. Well,
Earth mass is 10⁻⁶.
10⁻⁶, yeah. Yeah, so that would perturb orbits for sure, especially, I mean, that's roughly the heliopause, right? So it's in the local solar system, not even.
Right, it's within the orbit of Jupiter. I think we would know if something like
Yeah.
that flew through.
I would expect so. So, I mean, I'm not saying that this is going to be detected, right? On the contrary, I would say that this is telling you that the prospects for detection are low.
And the 10⁻³, sorry, that was for DM radio guts magnet.
No, that's for the MadMax. This is the
Okay.
MadMax.
Okay. But for that one, you would have what, like a parsec or something, if we got DM radio gut.
Yeah, I forget the exact number. There was a plot that was made of a bunch of different proposals for this review that we put out in January. I'm afraid I don't have it in the backup slides.
Okay,
So
but it
I
would
can
certainly be
send
a
it.
longer range, that's.
Yeah, the other interesting thing though is that, so the magnetic Weber bar concept is the only one that comes close to beating LIGO for PBHs. Actually, LIGO, if you were to extend its sensitivity to high frequencies, by virtue of its broad bandedness, can actually still be a very good detector for subsolar mass black holes. But that would require actually doing that extension to high frequencies, which for various reasons they don't.
All right, well, let's go ahead and thank Sebastian again. Okay, so I guess lunch and then we have triple club after, so maybe we should start later or something, or.
20 minutes is not so bad for grabbing lunch. I think that's good.
We can start whenever
Sorry,
everyone
when
gets
we get
back.
back.
Yeah.